Good afternoon. Today we will discuss about the next chapter after we discussing about the capacitance. This chapter is current, resistance, and direct currents or DC current. Okay. The first, what is the current? So, the electric currents, or simply we call it currents, is the key per dt. The key per dt. The key is amount of the charge in a closed loop in a time unit. So if we have or we want to create the current, we have to move the current from for we have to move the current, or the current have to flow from one, it's like this one, from this from this node to another node in the battery in the closed loop, and we measure it in unit of the time. It's like 1 second or another time unit. So this is the current. So it's only depend on how much the charge that flow in the cable or in the closed loop per unit of the time. So this is the current. So we simply, the current is 1 ampere is 1 coulomb per second. So to create a current, we need a battery or source of the voltage or source of the electric. So because of there is a potential difference between the anode and cathode in the battery, or the positive or negative battery, we can push the charge to flow from one node to another node. So the charge and the movement of charge, it means that the movement of the currents. Okay, so this is the current, and then the direction of the currents is similar to the direction of the positive charge carrier. So if we know that in the closed loop, or in some case like the electron or the negative charge flowing to like to left side like this ones, so it's mean that this is the charge movement, a negative, the charge movement. So the current will flow in the opposite direction, because the current flow in the positive direction. It means that if negative charge move to the left side, it's like the positive charge move to right side like this one. Okay, so the electric current, so we have to remember the Kirchhoff current like this ones. So in the Kirchhoff current, I0 is equal to I1 plus I2 here. So it's like this also another, this is the I0 is equal to I1 plus I2. Okay, so let's check this exercise. What is the I here? What is the magnitude and direction of I here? So the first the first one, we have to remember the Kirchhoff law, that the inside current is equal to the outside current. It means that this is the node here. So in this problem, all the node is similar to one node. So simply we can collect it together in one node like this one. This is the similar node. So check the current inside to the inside to the node is like this one, and then this one, and another one here. So this is the in is equal to out. So the current in is 2 ampere plus 3 ampere plus 4 ampere plus 2 ampere is equal to 1 ampere plus 2 ampere. You can see, or you can, you can see from this equation that this is a 5 plus 4 plus 2 is 5 plus 6 is 11 ampere. So this current for the outside is only 3 ampere. It means that if the in is must be out, is similar to out, so I must be here. So the I is equal to 8 ampere outside. So the I here is this one. Yeah, it's not very difficult to solve this problem, okay? And then what is the current density? The flow of charge through a cross-section of the conductor at a particular point. This is the current density. And then for each element of the cross-section, the magnitude of G is equal to the current per unit area. So this is the I, this is the current, and the current is integral of J is the current density, dot dA is the cross-section of the area. So I is integral of J dot dA, so J is constant, so we can move the J to the in front of like this one. So J integral dA, so it's equal to JA. So the J is equal to I per A. I is the current and A is the cross section of the conductor. So it's simply like that if we want to know what is the current density of the material. And then what is the drift speed if the current flowing in one conductor like this one? We have like the conductor has a length of L, the big L here, and the current flow in the left side. You can see that the positive charge is moved to left side, and then it's mean that the carrier is moved to another side. It means that we have the drift speed. Drift speed is speed of the carrier, the movement of the carrier from one side to another side. This is the drift speed. Okay, this is the drift speed. And then the charge or the key, the total of key is equal to n. N is the number of electron. Dot A is the cross section or the area of the conductor. The L is the length, and E is the unit of the electron. E is equal to 1.6 multiplied by 10 point minus 19 coulomb. This is the E. And T or the time is L per Vd is like a common use in it's like in our daily life. The velocity is equal to distance per time. So the time is equal to L. L is the distance and Vd is the drift speed. So we can get like this ones. So we back to the definition of the current. I is key per T like this ones. So we substitute the key using this equation, and A dot L E, and then per T is L per Vd. So we can get N A E dot Vd. And then so the Vd is equal to I dot A per N dot A dot E. And I per A here is the J, so Vd is J per Na, and then the G is the density, it's the current density. Or so the J is N E dot Vd. Vd is drift speed, and then N is the number of electron, and E is the unit of the electron. And then what is the direction? This the drift speed. The direction of the drift speed is equal to the direction of the current or direction of the positive charge, and also this equal to the direction of the electric field. You know that the electric field the direction of electric field is from the positive charge. If we have the positive charge here and the negative charge here, so the direction of the electric field is like this one. This is the direction of electric field. So it means that if the charge is moved from one side to another side, the electric field direction is equal to or similar direction with the positive charge movement. So the electric field direction is like this one, is equal to the direction of the current, and also the direction of the density, current density, is equal to the direction of the current. So please remember this one. So checkpoint second, the figure shows that conduction electrons moving leftward in a wire. Are the following leftward or rightward? A is the current, and B is the current density, and then the electric field E in the wire. So the first one, what is the direction of the current or I? The electron movement, the electron moving to the leftward like this ones. So it means that the current direction is opposite, in the opposite direction with the current movement. So the direction of the current is like this one. It's like a positive carrier or opposite way with the electrons. And then what is the current density direction? The current density direction, if you remember the previous slide, the direction of the current density is also equal to the direction of the current. And also the electric field direction in the wire also is similar to the direction of the current and also direction of the current density. Okay, like this one. Okay, so after we are discussing about the current and current density, and you know about the current density, and also the direction of the current density, and also the electric fields. Now we will discuss about the resistance and resistivity. In previous chapter, we have discussed about the capacitor, and the capacitor can store or can save the charge in the electric field. And what is the resistor? Resistor is like in bahasa Indonesia is the tahanan or the hambatan. It means that the resistor cannot store or save the charge. It's just like like a hambatan. So R in the circuit is V dot I. V is the potential difference between one node and another node in the circuit, and I is the current. So 1 ohm in the resistance unit is 1 volt per ampere, like this one. And then this is the resistor, you can see. And then every material has the resistivity. On resistivity depend on the material, like this ones. So the resistivity or rho is equal to E per G is electric field, and J is the current density. So the unit of E is V, volt per meter, and current density is A per meter square, ampere per meter square. So the rho is volts per ampere meter or ohm meter. So the ohm meter is the unit of the material resistivity. So you can see in table 26.1 there is some resistivity of the materials like silver, copper, gold, aluminum, etc. You can see it. And then the resistivity, another term related to resistivity is conductivity. Conductivity is like the opposite meaning with our antonym with the resistivity. So the conductivity is 1 per rho. So this also this is the resistivity, and you can easily see or calculate the conductivity of each material here. And then how to calculate the resistance from resistivity? So we note that E is equal to V per L. V is the potential difference, L is the gap, and then J is equal to I per A. I is current, A is area, and rho, we note that rho is E per J, so we can substitute E using phi per L and J using I per A. So phi per I is R, so it's equal rho is phi per I is R L per A. Okay, let I maybe not like this one. Okay, so this is like this one, so phi per L dot A per I like this one. Yeah, so is equal to phi per I dot A per L, so phi per I is R, so R A per L is equal to rho. So R is this one, rho L per A. Rho is the resistivity, material resistivity, L is the length of the conductor, and A is the cross section of the area of the conductor. So we can easily calculate the R if we know the material resistivity, the length, and the area of the material. In checkpoint 3, the figure shows three cylindrical copper conductor with their phase, area, and length. Rank them according to the current through them, greatest first when the sum potential difference V is placed across their length. So, what is the largest, the greatest currents through this conductor? The I is equal to V per R. It means that if we want to know or we want to determine the greatest current through A, B, or C conductor, so it means that the greatest current is mean that's the lowest R. So we have to check what is the lowest R. You can see here R is equal to rho L per A here for the first conductor, and then for B conductor R is equal to rho 1 per L per A per 2, and then CR is equal to rho L per 2 per A per 2, like this one. So here is similar, right? This is a similar. So A is similar to C. And then what is the B? So the B is a rho dot G L, yeah, per a half of A. So it's equal to it's like this one, rho dot 3 per 2L dot 2 per 1 A, like this one, right? You can check like this one. So we get rho 3L per A. So it means that compared to A and C, the resistance of the B is the largest or the greatest. So the I is the smallest. So the currents, the greatest current will be flow in A and C, similar, and then after that it is the B. So RA is equal to RC, and then smaller than RB. Okay. Okay, and then resistance and resistivity is they have the variation with the temperature like this one. So rho per rho zero is the resistivity in the in the 293 Kelvin, and then this is rho also this resistivity in that temperature, and then we can call A and T minus T0. We can see or we can know the resistivity in what temperature. It means that if we increase the temperature, like in this slide or in this figure, the resistivity will increase. And then this is the Ohm law, and then we have the plot. This is the resistivity resistor, like this one is like linear region, and this is the diode. We didn't measure the diode, so you can see like this one. So you can check, and then you can answer these questions. And then what is the power in electric circuits? Power, or P, is equal to I dot V, and then resistivity, P is equal to I quadrat dot R, and P, or power, is V quadrat per R. Okay, so this is the power density. And then semiconductor, we have the conductor and insulator, and in the middle of the conductor and insulator is semiconductor. You know that conductor is the material who can deliver currents or heat easily, and then its insulator is difficult to transfer the heat or the charge. And semiconductor is in the middle between the conductor and insulator. It means that we can change the conductivity of the semiconductor or the resistivity or the semiconductor by doing some techniques like doping. If you are electrical engineering, we will discuss in another course like this one. So in this physics, we just say that a semiconductor is a material that we can modify the conductivity or the resistivity of the material. It's like this is the pure of silicon. This is the resistivity of the silicon, and then this is the metal. So it's like this one. The resistivity can be greatly reduced in the control by adding a minute of specific impurities like a doping. So it's like this one. So we can modify the resistivity of semiconductor. And then we have the superconductor, and then the superconductor is just flow through a superconductor capacitor without losing its energy. It's like this one. And then resistivity by using the very low temperature, so the resistivity of the material become very low. So we can say that this is the superconductor. This is it's different with the conductor. Conductor, if the temperature increase, the resistance increase. But for in the low temperature, the resistivity resistance become so low. So we can say that this is the superconductor because of resistivity is very low. So this is the direct current of the material, and then there is I will talk about a little about this is the additional material here. Maybe you can see here. Okay, this is the definition of current. We have discussed in a previous slide. Also, this is the V, and then I would like to to highlight this one. This is the uh, how to check or how to make an equivalent resistance of the series. It's like R equivalent of the series resistance R1 plus R2 and plus Rn. And then for the parallel, it's like this one. So it is opposite with the capacitor, if you remember last chapter. And then every battery has the internal resistance, hence it will decrease the power in the circuit. So we say before that I is equal to V per R, or in this case, V is the A per R, but or R big R like this one. But in the internal battery has the small or the internal resistance. So we have to put another R here. What is the small r? Small r is internal resistance of the battery. So the total resistance of the circuit must be the internal resistance of the battery plus the another resistance in the circuits like this one. So it's like this one. We have the big R is 4 ohm, and then the battery has the internal resistance of 2 ohm. So the total of resistance is 2 plus 4 is 6. Okay, so you can see here. And then another exercise. Yeah, how to determine the equivalent resistance or resistance of this exercise. So first, we can start from the series component. So 8 per 4 is 12. And then for parallel here is 2 ohm. So 1 per 6 plus 1 per 3 is equal to 1 per R equivalent. So we can say that R equivalent here for parallel is 2 ohm. So this is the simplest series. So we can get this 14 ohm. Okay, this is the Kirchhoff law. Another Kirchhoff law is in the closed circuits like this one. So please remember, I think you have get this material in senior high school, but I want to remember. I want you to remember this one. If we have the circuit like this one, so first we have to determine the flow, the current flow of the circuits. So it's like we put or we start from this node. This is what first we get the A1, so plus A1. If we the first this is node and we go to this node, we meet with the negative, so this is the change to positive A1 minus IR1 here plus IR2 plus IR3. Then we meet with the positive, so this must be negative minus A2 minus AR4 and minus AR5, so it's equal to 0. And then another is the Kirchhoff. We discussed that before. I1 and I2, this is the inside to the node, is equal to offset the node I3 plus I4 and plus I4. Okay, so please check this exercise by yourself. And then how to determine the current in R1, R2, R3, R4, and R5, which resistance of 2 ohm, 2 ohm, 4 ohm, 2 ohm, and 4 ohm. Okay, you can see in this in the solutions. And then this is another additional material of the capacitor. So when switch is on, like this one, switch on, the capacitor is charged and will be stopped when the charge is full. So in the similar time, the current decrease, and then after we open the switch, the current will decrease to empty when J is fully charged. So this is the tau. Tau is RC. So we have to, if we want to know the maximum charge of the capacitor, so we have to calculate by using these equations. So Q is the charge in the capacitor is CE multiplied by I minus E minus T per RC. So CE is equal to Q, so we have these ones. And then the I is equal to E. E is the voltage per R dot A minus T per RC. So this is the current when the capacitor is charged. And also this is the maximum current, and then this discharge to another side if the switch is closed, if switch is open. So the I0 in maximum current is E per R. E is the voltage difference. This is like a V. So the tau, what is the tau? Tau is time when the capacitor when the charging of the capacitor is 63.2%. So it's like this one. This is the 63.2% of the fully charged. So this is the tau. Okay, if the fully capacitor is connected to the resistor, then a charge and a current decrease to empty. Yeah, we have to discuss about this one. And then this is the time constant, is the time indicator, which is the required to charge the capacitor until 63.2%. So tau is RC, like this, simply like this one. So this is the tau RC. Okay, this is the end of this chapter. See you in the next chapter. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.